Thank you for the introduction. Hi, everybody. We are the Responsive Thermal Energy Storage team. I'd like to first introduce you to the members of our team. Our advisors are Professor David Culler from the Computer Science Department and Ken Lutz, who is the Executive Director of the Multiscale Systems Research Center. Our project team is David Lewis and Andrew McKibben to my right. They are both MBA candidates at Haas, and I am Jay Taneja. I am a PhD candidate in the Computer Science Department. So there's a few important market trends that are guiding the need for and the adoption of energy storage in the electricity grid. First is the increasing amount of renewable energy that's being used to provide electricity. 38 of the 50 U.S. states have mandated a renewable portfolio standard whereby they set a target for how much renewables will be involved in the energy mix in the future. California, for example, has set a target for by 2020, 33% of its electricity will come from renewable sources. Now, one important factor when considering these renewable sources is the notion that there's the variable supplies. So solar and wind, the supply can't be controlled, and so energy storage can play an important role in mitigating the impact of the supply variability. Second is the high cost of providing energy at peak times. Take PG&E, for example. In the peak electricity parts of the year, the 1% of hours where electricity is at its peak, 10% of PG&E's capital costs are tied up providing electricity. So the utility would gain much value from being able to shave that peak consumption and move it to off-peak times. Energy storage has an important role to be able to provide that functionality. Third is the growing adoption of time-of-use rate structures, whereby consumers pay different prices during the course of the day for electricity based on demand on the grid. The most simple one is just where there's a peak period of the day where electricity costs more than the off-peak period of the day. There's value here for storage because utilities can benefit from moving that peak to, they can better reflect their wholesale electricity costs, what they pay for electricity, in their rate structures to consumers. And consumers who are savvy can actually move their consumption from those peak times to off-peak times and thereby save money on their electricity bills. So what our technology does, our technology uses freezers to enable cost-efficient, distributed, and highly scalable energy storage that provides a range of services to electrical utilities, as well as providing cost savings to end users with no behavior or service change necessary. So how do we provide that? Well, our technology was developed using the observation that conventional fridges already have a form of energy storage. This is the thermal mass of the contents inside the refrigerator, the air and the items inside the refrigeration unit. This storage can be enhanced by inserting a phase change material into the freezer. Now, there's two parts in how this enhances the storage. One, you have increased thermal mass, which makes the swing of the temperature slower, so you need less energy. And second, by having it be a phase change material, you can actually absorb a large amount of energy through that phase change, through the freeze-thaw cycle of that phase change material. Coupling this with a programmable, embedded communicating controller to operate the compressor, you end up with a low-temperature ice battery. That's essentially a callable resource to absorb or emit energy, and it's a resource that allows you to essentially delay or advance compressor cycles and shape your electricity consumption schedule. So what are these modified freezers? How do they operate and how do they interact with consumers? So as I explained earlier, freezers have a predictable and periodic electricity use. This is a graph that shows essentially the temperature over the course of a day and the power used by a freezer unit. And you can see that it's generally a constant throughout the day. And also, as I explained, most consumers, as of now, pay one price of electricity all day, so that this periodic usage is spread out over the entire day, and so the cost is the same. But as we switch to time of use rates, where there's a peak period of the day where electricity actually costs more, we can take advantage of this. Using our technology, we can actually make the unit aware of when electricity costs are higher, as well as what time of day it is, and it can use electricity according to that rate schedule. So this limited amount of information, just knowing what time of day it is and what the rate structure is, you can actually save quite a bit on your electricity bill. So there's another value that you can gain from aggregating these modified freezers, and that is through the grid ancillary services market. So on the electricity grid, there's essentially a set of markets that sell a portfolio of electricity resources that are used to balance grid supply and grid demand. This is utilities purchasing this resource from the market, which is operated by the balancing authority, like CAISO, and this portfolio of resources are to equate supply and demand on both short and long-term timescales. So some basic examples of how this would work. So here you can imagine a snapshot of the state of California. At any point in time, across the population of refrigeration units, some proportion of them are actually operating. This proportion actually reflects the duty cycle of the compressor within the unit. So let's say you had a generation shortage at some point in the day caused by maybe a cloud system that wasn't seen and the solar energy drops in the grid. Well, the system can respond to that by sending out a signal to the compressors and turning a number of them off. On the other hand, let's say you had a surplus of energy that was available because it was a very sunny or unexpectedly windy day. The number of compressors can be turned on to soak up some of that extra electricity. The third scenario is if you're aiming to peak shave, and this would be in advance of a high electricity usage day. The night before, you can imagine turning on a number of the compressors, and then during the course of the day, when electricity demand is high, those compressors can remain off, and that generation that would have normally provided the electricity for those units is no longer needed. So I've discussed a little bit about the applications that this technology has. I'd like to compare our technology to other types of energy storage technologies that are available. So for one, our technology is distributed as opposed to being centralized. The refrigeration units are spread throughout the electricity grid, and the advantages here are that you can avoid constrained electricity transmission by having resources available at the edges of the grid. This is very valuable to utilities. And the second advantage is that you've already converted this electrical energy back to thermal energy, and you do not have to convert it back to electricity, so you don't lose that efficiency. Second, this is an extremely scalable technology. It's not difficult to add additional units to the pool of resources, and so by using that aggregation, you have a wide range of services you can provide. Third, there's no behavior or service change necessary to use this technology. So customer friction to introduce this technology into their devices should be lower based on that.
So given what our technology can do and its competitive advantages, it's important to understand how it fits in the current market environment. So at its most basic level, as a means to reduce peak energy consumption and cost, our technology generates value to each of the parties involved. So for utilities, they benefit from lower capital costs associated with more balanced demand. So generating peak energy is very expensive, and even a minor reduction provides a lot of value to the utility. End users on time-of-use rate schedules clearly benefit from lower electricity bills. And as a technology provider, along with potential partners, you would share in some of those cost savings that you generate. But it's important to understand what those savings actually are. So in this example, we took a typical residential consumer and a typical commercial consumer in California. And we built a bottoms-up model based on PG&E's time-of-use rate structures to understand what the actual savings would be from completely shifting peak consumption to partial peak and off-peak times and rates. And as you can see, the savings are substantial. So on the residential end, that's a 16% reduction in the cost to operate a refrigerator. Commercially, it's about 15%. And what's important here is there's no behavior change and there's no performance change. So that's business as usual, but 15 to 16% cheaper. Now, as you project those savings out to a larger scale, like statewide, for example, you can see that the potential depends heavily on actual adoption of time-of-use rate structures. And right now, that's relatively low, particularly on the residential side. So the savings there is only $3 million. Commercial, it's a little bit better, 30% and $22 million. But what's important is that adoption of time-of-use rate structures is increasing, and that's especially on the commercial end. That's one of the areas utilities are really focusing on. So if you broaden that out to 100% adoption, you can see the potential is actually large there. I don't know if you ever get to 100%, but it's definitely moving in that direction. The other potential application for this technology, as Jay mentioned, is grid ancillary services. Now, the way this market works is utilities purchase ancillary services through an ancillary service market typically run by a balancing authority like CAISO. And the way our technology would work is, or would apply here, is that an aggregator would essentially aggregate control over end user compressors and sell that control into the market. So for example, an aggregator would sell the ability to reduce, say, 1 megawatt of demand by switching compressors off into the market at a specific price and for a specific time period. Now, if a utility agrees to that price, they pay the aggregator through the market, and the aggregator shares some of that revenue with the end users. Now, the aggregator is contractually obligated to actually switch off those compressors during the specified time frame should the utility request it. Now, they're paid regardless of whether or not the request is made, but the point is they are obligated to either switch them off. Now, utilities benefit through lower capital costs to provide ancillary services. This is cheaper than generation. And ancillary service markets benefit because they can avoid having to purchase energy generated through fossil fuels. So this will help them better meet renewable portfolio standards. And end users clearly benefit because there's no behavior change needed there. There's no performance change in the refrigerator. They're just now getting paid. But there's a range of ancillary services, and as this technology is developed, it's important to understand where it best fits in this market. So in general, ancillary services can be thought of as a continuum based on responsiveness. So on one end, you have capacity curtailment, which is slower responding. On the other end, you have frequency regulation, which needs to be very responsive. And in general, the value like on a megawatt hour basis is correlated with responsiveness. So frequency regulation, megawatt of frequency regulation is more valuable than capacity curtailment. So in assessing these different options, we used 3 basic criteria. One was just the general competitive environment. The second was market size, and the third was our technological advantage. So in terms of day ahead and capacity curtailment, these are relatively large markets, and there are already relatively large competitors, incumbents there, such as Converge and Enernoc. And we think it'd be very hard to enter those markets and compete with such established players. And in addition, our technology is not, we feel that it doesn't offer a significant advantage over current technologies used there on the demand response side to really give us an advantage over what's currently being offered. In terms of spinning reserve and non-spinning reserve, those are smaller markets, and they're also markets where non-generation resources have traditionally lower participation. So if you look at what our technology can do well, in particular its responsiveness and the ability to turn off compressors and turn them on, that aligns really well with the requirements of the frequency regulation market. Responsiveness is important, as is the ability to go up and down. And so that's where we think our technology would be best positioned. Now, looking more closely at the frequency regulation market, it's not terribly large, but it is growing quickly. And I think California is a good example of how and why that's occurring. Over the next decade, the market is expected to roughly double. And that's primarily being driven by California's push to 33% renewable portfolio standards. So in support of that push, the state forecasts that they will need to roughly double the amount of regulation, the regulation capacity requirements. And it's easy to project this trend out to other states or countries where there is a large push to adopt renewable resources. So the market is not big, but it's growing quickly. But it also requires relatively stringent technological and operational requirements to participate. And we think those are hurdles that our technology can meet. So in particular, the response time of less than 1 minute and the minimum bid requirement of 500 kilowatts. We can address the latter through aggregation, and given how responsive our technology is, we can respond in under a minute. And finally, the duration required, which is basically how long you have to either have your compressors on or off, is at maximum 60 minutes. And we think that aligns particularly well with our technology and given who our end users are. So regardless if our technology allows an end user to turn his compressor off for 8 hours or 4 hours, it is food storage. And there will most certainly be a concern around food spoilage. So having a maximum duration of 60 minutes would likely alleviate that concern and make adoption of this probably a little more feasible.
Thanks, Andrew. So at this point, we've demonstrated the tremendous value of our product. We've also identified 2 attractive applications in peak cost avoidance and frequency regulation. But questions still remain about in which refrigeration markets we want to build this capacity, and also how do we want to deploy our technology to those markets. We can either retrofit existing refrigeration units, or we can go with a replacement model by which we partner with an appliance manufacturer to embed our solution in their technology. Now, in looking at the residential and commercial refrigeration markets, they're both very attractive in terms of their total annual energy consumption. However, there are key market characteristics that inform which deployment strategy we should use for each of these markets. On the residential side, our discussions with appliance manufacturers showed that any sort of retrofit would very likely violate their warranty. So the only option to deploy our technology in this market is really through a replacement strategy. On the commercial side, it's a different story. Retrofits have much less of a chance of violating warranties. In addition, the commercial market is more fragmented and with more highly customized units. So partnering with one appliance manufacturer to penetrate the commercial market would be much less successful than it would be in the residential market, which is why we believe we should pursue retrofits on the commercial side. Now, based on these 2 deployment strategies for the commercial and residential markets, we believe we can much more quickly build meaningful capacity via commercial retrofits. Again, our discussions with appliance manufacturers show that they have an 8 to 10 year technology development cycle to design a new residential refrigerator. So if we want to embed our solution in one of their new products, it's likely that we wouldn't be able to hit the market for at least 8 years. Then again, on the commercial side, a different story. Because we're retrofitting existing refrigeration units, we can avoid this lengthy technology development cycle. In addition, because more of the end users are on time-of-use rate schedules, there's an immediate and substantial value to those end users to the tune of approximately $500 for your typical walk-in freezer per year. Therefore, we believe the best short-term opportunity to build capacity is in commercial retrofits. Now, when looking at a go-to-market strategy, in the short term, our strategy is really driven by the fact that we can build capacity quickly via commercial retrofits. Again, because 30% of the customers are on time-of-use rate penetration, and that number is increasing, we believe the best short-term application for our solution is peak cost avoidance. In addition, as Jay said, this requires less of an investment in the communication for the device. Looking ahead to the future, the RPSs that are enacted today will increase the renewable fleet in the future and thus increase the need for ancillary services. In addition, FERC's proposal for pay for performance means that more responsive ancillary services in the future will be valued higher, such as our solution. So we believe that the long-term play is to take this customer base that we built up in peak cost avoidance and apply their capacity to the frequency regulation market. In addition, this longer-term time frame lets us leverage an investment in communication that will be made in smart meters and home area networks. Now, in conjunction with our go-to-market strategy, there's also patent and licensing decisions that need to be made. On the patent side, we believe we should start the UC Berkeley process by filing an invention disclosure. UC Berkeley would then file a provisional patent, and we'd have approximately a year to decide in which geographies we want to protect our technology. In the meantime, we also need to make a decision on licensing. If we decide to start our own business, we would likely be the ones to sign an exclusive license with UC Berkeley. We can also partner with an incumbent technology manufacturer who would be the one to sign that exclusive license. A third option would be to try and proliferate the technology and get it out into the market via many appliance manufacturers. And there's 2 paths here. One is to encourage many appliance manufacturers to sign non-exclusive licenses, and the second option is just to publish the technology publicly. However, this last option comes with risks, as often an appliance manufacturer will set up patents around a public technology to deter their competitors from adopting the technology. So this last option does come with the added risk of having unintended consequences and not actually proliferating the technology. So to summarize our recommendations from today, we believe that the best short-term application of our product is in peak cost avoidance. In the long term, we want to take that customer base and their capacity and move into the frequency regulation markets. Our target customer base at first will be built via commercial retrofits, and in the long term look to target the residential market through a replacement strategy. Now what this means for our technology is that we'd like to see commercial freezer prototypes built and also ensure that the communication for this device can meet the responsiveness and protocol requirements for the ISO's frequency regulation market. And lastly, we want to begin the UC Berkeley patenting process, and as the technology continues to develop, think about what we want our long-term deployment strategy and licensing strategy to be. So we thank you all for your time today, and at this point we welcome any questions you guys have.
Hello? Okay. I'm glad to see that you went to the manufacturers, and I would be curious which ones you went to, because one of the major ones got in trouble about 15 years ago with all their compressors burned up, and they had a huge bill because of something that was done on the transmission lines. So I was curious that you were doing that, and what kind of feedback are they're giving you, because you know, turning on a compressor and off, it produces a lot of transients and some other issues, and I was just curious what their feedback was of letting you do that.
So our experience was through an interview, essentially. We interviewed one of the large appliance manufacturers, and the result of that was more of a view that residential units couldn't be modified in a retrofit fashion because it's difficult to interrupt first of all, one big concern for residential units is volume, so that made it very difficult for our product to be a viable solution there. As far as compressor usage, with commercial devices, they're actually a lot more flexible, that they can change their duty cycle quite a bit and run quite a bit more. With residential, the nice thing here is that you only need to extend the cycles at night briefly. You actually don't need to change much of the operation other than extending them slightly longer. So we didn't ask that question specifically, but they made it clear that it's possible to extend those cycles slightly and make that how our technology is adopted.
So you talked to a foreign manufacturer, you didn't talk to one of the big 2 or 3 domestic, is that correct?
That's incorrect. We talked to GE.
Okay, because I talked to them about this issue.
Oh, I see.
Well, a phase change material is effective basically at one temperature, like water changes phase at 32 degrees.
Right, correct.
So this would mean that, in other words, you would have to have your the setting of your thermostats would be critical, because you would have to have it set below the phase change as opposed to above the phase change, which
Absolutely.
would mean you would not really want the users to be able to adjust the thermostats. And I wonder if you might expect much user resistance from eliminating the thermostats in the refrigerators.
Sure, that's actually a very valid point, and there would be limited control on the user side of the thermostat because the temperature requirements for this phase change material are very important. So we've selected a phase change material that fits the regime of temperatures in which the device would be operating. So reducing that is important. It's something that we would have to minimize. The important part of that is essentially a lot of the devices don't actually vary terribly much in how much control you have over the temperature. It's a few degrees, and so we would be minimizing that. It's true.
So I mostly have a clarifying question. I think the phase change material is actually pretty important here. It sounds like balance of system, the controls and so on, you have pretty well wired, pardon the pun. But on the phase change side, I'm curious how much IP, potential patentable IP you have here at the university for this. And also, have you done any kind of preliminary look at what's already been patented? I suspect this application has been thought of before. Having given you those sort of cautionary questions, and I do want to hear your answer, I want to just volunteer. I think this is potentially a very compelling solution.
Yeah, so we haven't done a great deal of research into what's been patented before, and with the phase change, you can patent the phase change or you can patent the process around the phase change. And I think it's one we'd probably look into, given that it may not be a very complex, we want it to be a cost-effective, easy-to-obtain material. I think we would look more towards the process around the phase change rather than the phase change just itself. Does that make sense?
Yeah, I'm curious to know how in residential refrigerators this would interact with the defrost cycle.
So the question was about the defrost cycle. Defrost cycle is essentially once a day. It's a slight heating so that the frost doesn't form in the freezer. So defrost cycles are another important target for, we spoke with GE, and a very important target for them to be able to schedule the defrost cycle so that it moves to off-peak times. It would be, if we were working with residential refrigerators, it would be very important to make sure that the two systems didn't occur at the same time. You want to move defrost cycles off of peak. This is one thing that GE is already looking at quite a bit, is moving those defrost cycles to times when they won't be affecting peak electricity load.
But doesn't the temperature of the freezer have to rise in order for the defrost cycle?
Yes. So
you would have the ballast of the phase change material holding the temperature from rising.
right. So the important part about the defrost cycle is, one thing is where the temperature rises. It's meant to be closer to where that defrost fan is. And second of all, the third component, the ice battery here, is meant to be thermally isolated. So you need a casing that prevents that from. So you'll need to. It's essentially an active unit that you release temperature from it. You release thermal energy from it on demand.
I'm over here. About what fraction of volume of my freezer do I have to give up if I want to do either peak shaving or frequency regulation?
Sure. So in one of the initial slides, we showed that giving up so we took a normal residential refrigerator about 16 inches by 20 inches, and you give up 1 inch of the freezer in height, that provides you 1 kilowatt hour of electricity, and that 1 kilowatt hour can actually buffer about 20 hours of operation for your refrigerator, which is about a 50-watt average load.
Also to that question, our discussion with GE showed that after the cost of the refrigerator, the capacity of the refrigerator and the freezer were the most important aspects for a potential purchaser. So it's something that you have to balance how big you want the battery to be versus whether it'll deter a customer from actually purchasing the refrigerator.
In walk-in freezers, retrofits in commercial settings, that is much less of an issue because we spoke with some providers of walk-in freezers, and generally those spaces aren't quite as utilized, so there's a lot more freedom to add volume.
You had a slide that showed the revenues for both, respective revenues offset for both residential and commercial. Given your commercial focus, and I apologize, you may have already gone through some of this and I missed it, but could you go through the unit economics a little bit, your sense, because you've got obviously the price of the materials, but then there's probably a fair amount of installation and retrofit cost, and then there's grid integration cost along with system control cost allocations. And so if you could just kind of give some sense as to how you see those unit economics playing out.
So yeah, we really have not looked in depth at the cost requirements, or the cost of doing this. We know that installation, for example, would be something that would be costly. So on the residential end, that's almost kind of a non-starter to pay for someone to go out there and modify a refrigerator. I think that what we showed were the potential savings, and that's more of a target for us to use in terms of what, from a cost standpoint, what are our boundaries. So I think that's kind of how we're thinking about this point. I mean, we're well away from figuring out actually what a unit would cost to manufacture and develop and the cost of the phase change and installation. But we do know that based on the savings it generates, that's kind of an upper bound, that or a multiple of that would be an upper bound of how much the actual unit could cost to manufacture.
Maybe I missed this, but in order to have a material impact on the grid conditioning and peak shaving, what kind of installed base do you need, especially in certain densities and certain geographies?
So we got a penetration slide, and to have a material impact with residential refrigerators, that's about 500,000 installations, which is very large. On the commercial end, it's much lower. It's about 11,000. So it's still significant, but it's by a factor of 50 less than residential.
Sorry, we're going to have to cut it off. They keep going, but great questions, and I'm sure the team will be available for more later on.